Okay, and we're going to turn on transcript. And here we go. So, the restrictions on X mean what can X not be. There's other ways of saying it, which is why it gets kind of confusing. But basically the game is the denominator can never equal 0. So we just make that equation up out of thin air. The denominator can never equal 0. Now what happens is we pretend that it does equal 0 because that's how we're going to solve it. That's what we studied all in chapter 7, how to solve it. Okay, so we solve this. We use the AC. AC is -6. What times what makes -6? That's -5. That's -6 times 1. So we say 2x squared minus 6x plus 1x minus 3 technically equals 0. Okay, we slap parentheses around the first two and the last two, leaving the plus in the middle. Take out a 2x here, leaving x minus 3, plus, can't take anybody out, so we say we can always take out a 1, also leaves x minus 3. Remember, the fact that those x minus 3s are the same, that's your check. That's how you know you've done something right. If those two are not the same, then you screwed up. Somehow you screwed up, or I screwed up because I gave you a problem that doesn't work. But those two have to be the same. After you factor somebody out of that one and factor somebody out of that one, then those two have to be the same. Then what we did is we pulled the x minus 3, excuse me, in front, or I did. Everybody else in the world is wrong. And 2x plus 1, and we say we're back to it equals 0. So we split it up. X minus 3 equals 0, or 2x plus 1 equals 0. Solve each of those. We get x is worth 3, x is worth -0.5. Now, I'm not done with this problem by any long shot, okay? But so far, is that okay? This is a little bit review, so I talked a little bit fast. Do you need me to explain anything? Is there any step here that you don't like? Again, keep in mind, we're not quite done. Is there anything you want me to explain? How did I factor this trinomial? How did I use the AC? How did I solve what I called the baby equations? Solve the babies. After you split it up, we solve the babies. Okay, I don't hear anybody yelling at me. So now, here we go. Remember, we start by saying the denominator cannot equal 0, ever. But we pretend mentally that it does, because that's how we know how to solve. But then we just go back and say, oh yeah, it can't equal 0. It can't equal 0. It can't, it can't, it can't. So all those equals turned into not equals. Okay, and then our restrictions become x cannot equal 3 and -0.5. That was our restrictions on this problem. Okay, different books have different ways of asking this. Sometimes they say, what are the restrictions on x, like I did here. Sometimes they say, what values of x make the problem undefined. Undefined becomes a key word there. What values of x make it undefined? Undefined means the denominator is worth 0. Okay, And so what makes the denominator 0? And so those are called restrictions. So it's like heads and tails. Same question, just different ways of asking it. But anyway, that's the problem that we did last night. State the restrictions or find the values that make it undefined. Any questions on problem number 1? Anything? You're sure? Okay. Then coming over here to number 2, we want to simplify completely, reduce or simplify. We use those two words synonymously, reduce, simplify. They mean the same thing, almost the same in algebra. So the first thing we do is factor. Again, I'm going to skip steps. I'm simply going to factor this. Okay. And then if you want me to show how I did it, I will be happy. Oops. Assuming I can do it right. I will be happy to show you how I did it. But the numerator is what I call an easy trinomial. Easy because the coefficient of x squared is a 1. That made all your work easier. You didn't have to go through half of this crap over here. Okay, just easy 1. So that was a trinomial. It factors into that. The denominator was a dose, difference of 2 squares. It factors into that. Okay, then we start canceling. Now, these two factors are not the same. X minus 2, 2 minus x, they're not the same, but they're close enough that that's what I call that -1 trick. Okay, x minus 2 and 2 minus x technically are not the same, but they cancel mostly and leave a -1. Now, we debated last night, I debated with myself and lost. Where do you put the -1? You can leave it in the numerator, you can leave it in the denominator, or you can put it right in the middle. Okay, so I'm going to put it right in the middle for now. And we have x minus 5 and 2 plus x. Okay, those are left over. Remember, there are invisible quantities, invisible parentheses around the numerator and the denominators. Okay, that's to stop you from saying, oh, look, the x's cancel. No, they don't, because these two are not the same. If you haven't noticed, canceling or reducing only happens when the problem is a multiplication and division problem. See, these two are multiplying. These two are multiplying, and the top and bottom are dividing. But here, if you look at this, the numerator, they're subtracting. The denominator, they're adding. Canceling only happens with multiplication and division. Okay? You can only cancel the quantities. So anyway, that's kind of a brief review of section 8.1. We talked about how to reduce something by factoring everybody and their mother. We just factor everybody and then cancel out who cancels out, whatever. And we also talked about restrictions on the domain or restrictions that make it undefined. So those two problems there. Okay, any questions on either of those? Do you need any help, any explanation on factoring these two original into these? Okay, then I need to erase this. And the next thing we talked about was multiplication and division. Okay, this is restrictions, this is reducing. But then the next topic was multiply and divide. Okay, so I need to erase. Okay. And let's do this one, and then we'll do one more after this, but I want to leave room. So this is number 3. And when I give you the exam, it will say perform the indicated operation. And in plain English, that means either add, subtract, multiply, or divide the fractions together, because that's what we're going to talk about eventually. When the test comes, exam number 1 comes, I'm going to just give you a whole bunch of things. Some are going to be addition, subtraction, multiplication, division. Some are going to be reducing. And it's just going to, the instructions are going to say, hey, do what it says. If it says add, add. If it says multiply, multiply. Okay, so here we go. This one's going to be x squared plus 2x plus 1 over x squared minus 1 times x squared plus 3x plus 2 over x squared plus 4x plus 4. So this directions say perform the indicated operation. This operation is multiply, so multiply these two together. Check your notes. You'll notice last night we cheated. We very seldom multiplied them together. What we really did is canceled. We reduced. So take a few minutes to work on that. So here we go. Again, I'm going to do the factoring in my head, but if you need an explanation, always feel free to ask. I'll be happy to show you. This one right here, the numerator becomes x plus 1, quantity x plus 1. The denominator becomes x plus 1 times x minus 1. It was a dose. The denominator is a difference of 2 squares. The numerator was a simple trinomial. Times. Over here, this is x plus 2 times x plus 1. The numerator became x plus 2 times x plus 1. The denominator was x plus 2 times x plus 2. Okay, so a whole bunch of trinomial factoring, a whole bunches of it. Okay, and then there's a dose problem. So now we look to see who cancels. Okay, x plus 2 with x plus 2. Nobody ever said they had to cross cancel. They can cancel on top of each other. That's fine. Okay, x plus 1, x plus 1. Okay, nobody else cancels out. Nobody else cancels out. These are not the same, okay, at all. So this is what we're left with, is on top we had x plus 1 times x plus 1. On bottom we have x minus 1 times x plus 2. Now, general rule of thumb, we didn't get to this last night, but it is multiply out the numerator. Leave the denominator factored. Multiply the numerator out, leave the denominator factored. Sometimes mom will allow you to leave the numerator in factored form, but multiplying it out, okay, this is where we use that matrix box or whatever trick you use to multiply those two together. Those two become x squared plus 2x plus 1. And then I said leave the denominator factored, so we can leave it as x minus 1, x plus 2. Am I in the glare? Just barely. So that is our final answer. And again, I skipped steps because I didn't show you how to factor, but I'll be happy to show you all of that. Is that okay with everybody or not okay?
Yeah, that's good.
Okay. One person says it's good. Okay. Guys, I'm trusting you guys to yell out. Remember, nobody can see you. That's one of the nice things about working on Zoom is you can shout out your questions and nobody sees you.
Or Professor, can we write down as, cause like, oh, you know what? Never mind. That was a dumb question. Never mind. Never mind.
No.
I figured it out right away.
Okay. All right. Anybody else have a good question or a dumb question? It doesn't matter. Anyone? All right. We're going to do one more problem and then we'll get into new stuff. One more kind of reviewish problem. Again, I'm shocked that no one's asking me how to factor these. Okay. Same instructions. Well, yeah, same instructions will work. But this time, the problem is intended to scare you. I'm going to do it. I'm going to write the problem in such a way that you're going to go, oh God, I don't know what to do. Stop and think. Okay. So on number 4, suppose f of x is equal to 2x minus 6 over x squared minus 8x plus 15, and g of x is worth 2x plus 10 over x squared minus 25. So we're back to functions again. F of x is a function. This is it. Okay. G of x is a different function. This is it. Okay. I want you to find f of x over g of x in simplest terms. Okay, now I'm going to get you started on this in a minute because I don't want you to just sit there and stare at it and do nothing. Okay. You guys aren't comfortable in general. Most students aren't comfortable with f of x and g of x. Okay, that's why I keep pushing up there so you get more comfortable with it all the time. But then when I put it in fraction form, okay, all of a sudden you kind of wet your pants and go, oh my God, what do I do? I put this on top of this? How? But wait a minute, before you panic, remember, what does the fraction bar actually mean? It means f of x divided by g of x. So just because I wrote the problem as a fraction is another way of saying division. So f of x divided by g of x, okay, we did that last night. So this is f of x divided by g of x. So now I'll pause while you guys work on that. Okay, so while the recording was turned off, I took the opportunity, instead of saying f of x divided by g of x, I wrote down what f of x actually was, divided by, I wrote down g of x. And then we learned that in fractions, we've known this for years, to divide fractions, you change the division symbol into multiplication, and you flip over the second fraction. Now that's all arithmetic. But now we got to get to the algebra part of this, and the algebra part says factor. So we have to be able to factor everything. So to factor 2x minus 6, factor out a common 2, that leaves x minus 3. X squared minus 8x plus 15 became x minus 3, x minus 5. Boom. Times x squared minus 25 was the difference of two squares. It became x minus 5, x plus 5. And 2x plus 10, you could factor out a 2, leaving behind x plus 5. So, any questions on my factoring so far? On actually any questions on any step on how I went from fractional form to basic division, and then substituted in place of x, f of x, I actually put what the polynomial was, or the rational expression, I should say, was. It was division, so I rewrote it as multiplication with a flip, and then I factored. I did a whole lot of work up there. Any questions on it? Okay, then here comes. Who cancels out? Well, the x minus 3's cancel. This x minus 5 cancels. Okay, these x plus 5's cancel. Now, we need to be careful. When we say they cancel, they technically cancel to a 1. If you have x plus 2 over x plus 2, well, we know from arithmetic that anything divided by itself is 1. So when we're canceling it, we're basically saying it equals 1. And we're saying that in most cases, 1 doesn't matter. Okay, so these cancel and make 1. These cancel and make 1. These cancel and make 1, whichever cancel. So when you multiply all this stuff together, okay, everybody canceled. On top, you have 2. On bottom, you also have a 2. Well, wait a minute. What's 2 divided by 2? On top, we have a 2. Bottom, we have 2. I get it out of the glare. I'm sorry. So anybody divided by itself, the final answer is 1. This whole fraction, this divided by this, okay, eventually when we went through all the work, canceled out everything, simplified down to just a big fat 1. My concern on this is a lot of people say, oh, they all cancel out. Everybody and their mother cancels. So I have nothing left. And so people write 0 because you have nothing left. That's not right. When things cancel, they technically cancel to a 1. So you got 1s times each other on top, 1s times each other on bottom. 1 over 1 reduces to 1. So be careful of that trap. Okay, we say cancel, we mean reduce to 1, but we're all lazy. We just say cancel. Any questions on that problem? Okay. Again, the intent of the problem was I had multiple reasons for it. One is I wanted to review the function notation f of x, g of x. 2, I wanted to scare you with some function notation with division, okay, but show you that it's just not that bad because a fraction bar is actually a fancy way of saying division, which is what we studied last night. And then, of course, I wanted to review the division. Okay, need to erase, go on to new stuff. Anybody have any questions before I erase? All right, here we go. Couple things I'm going to erase over here. I am taking roll tonight, okay, at the end of class or near the end of class. So Bach, this time I hope you're there when I in class. Okay. And tomorrow night we'll have a tiny quiz right at the end of class. You may use your notes tomorrow night. Okay, it's 3 or 4 problem quiz. You can use your notes tomorrow night in class.
I'm here the whole time, Professor.
Okay. But when I said it ended, you were still on there for about 10 minutes. I finally gave up. All right, here we go. So we have talked about in chapter 8.1, okay, we talked about restrictions and reducing or simplifying. In chapter 8.2, we talked about multiply or divide. So what's left? Add and subtract. And that's chapter 8.3 and chapter 8.4. And then, of course, word problems and equations and stuff like that. So in chapter 8.3 and 8.4, we talked about add and subtract fractions. Remember, all of this is all about fractions. Okay. To go back way back to whenever you were introduced to fractions, the key to adding and subtraction is they must, and I cannot stress that enough, they must have the same denominator. Okay, I just can't stress that. That is just a fundamental truth at all levels of math. There's no, not, when you get to a higher level of math, do we have another trick that we show you where we violate this rule? No, this rule is fundamental. If you want to add and subtract fractions, they must have the same denominator. Okay. Well, we'll talk about that in just a moment. And then when you do it, the basic thing is you either add or subtract the numerator. I'm going to actually make it, I'm going to say the tops together, and you keep the denominator. That was the fundamental rule. Okay. So you added and subtracted the tops together and you keep the denominator, whatever it was, and possibly reduce. Okay. Not all fractions reduce, but now reduce comes up here. We've studied reducing in algebra. So now we're going to add and subtract, and it's possible that our answer reduces. A simple example from arithmetic. Suppose you have 3/8 plus 1/8. From arithmetic, they have the same denominator. So mathematically, we say 3 plus 1, add the tops, keep the bottom. Okay, well, 3 plus 1 is 4/8. And that's the right answer, but it's the wrong answer. Okay, you've done everything properly. You added the top numbers, 3 plus 1 was 4, and you keep the denominator, 8, just keep the 8. But the reason it's wrong is it reduces. Okay, it reduces, just plain old arithmetic reducing. Okay, you can divide top and bottom by 4. So this reduces to 1 over 2. That is the right answer. So two fractions originally did not reduce, but when you added them together, it turned out to be the answer does reduce further. And this is, remember, this is arithmetic. So we have shortcuts for arithmetic. For algebra, we don't have shortcuts. Okay, they're just ugly. So, okay, let's do a couple algebra problems and see how we do this. We're going to start with simple ones, and then we're going to move into more complex ones. All right, here we go. Is there anything I've said that you need clarification on? Anything that doesn't seem right? I know what I want to add here. And when we multiply or divide, the number one thing was to factor. When we reduce or simplify, the number one thing was to factor. Okay. So down here, when I write the word reduce, what I really mean is factor it. Because that's how we do it in algebra, not in arithmetic, in algebra. So be very, very, very careful. Make sure I would make like 3x5 cards of these steps with maybe an example of each one, a really good one from your homework or from my notes or something like that. So first example, 2x plus 7 over 4. No, over x plus 3 plus 5x plus 2 over x plus 3. So you go, oh, well, they have the same denominator. Okay, they already have the same denominator. So I can jump to this step. I can add the tops, keep the denominator. So in adding the tops, I have 2x plus 7 added with 5x plus 2, keep the x plus 3. Now, I know most of you will do that in your head, and that's fine. But what you're following the rule, and I just want to make you aware of what's happening in your head. The rule says add the two numerators together. So we end up with 7x plus 9 over x plus 3. And it turns out that that particular one does not reduce because it does not factor. Nothing in that problem factors, so it doesn't reduce. And that's about the easiest problem I can give you. Okay, add or subtract the numerators. Well, it gets a little messier. What if I gave you something like 4x plus 3 over 2x minus 1 minus x minus 8 over 2x minus 1? Now this is a little bit trickier. I'm gonna pause for a minute while you guys look at it, maybe think it through. Then I'm gonna do it. Okay, but this is a little bit trickier. So the trick is this minus sign. You should write on somewhere on your notes, I hate subtraction, because subtraction will always screw you up. But the reason I laughed is I taught AP calculus at Poway High School for 15 years. And when they gave the AP exams, they would give it in the library, and because we had so many students taking calculus. And I forgot, usually I meet with them in the morning, I give them some orange juice and something to eat and make sure everybody's okay. And we all talk, and I try and keep them from being too nervous. And one time, just before they went off, they were already in the library, and I'm going, oh crap, I forgot to tell them. Two things. There's two things was my mantra. Okay. One was I hate subtraction. And the other is there's a setting on your calculator when you get to calculus called radian mode. Radian, R-A-D-I-A-N. And I'm going, oh, I forgot to warn the students to change your calculator, and I forgot to remind them. So I went running out, and I went running around the library, because there were all kinds of rooms in the library. And I went running around yelling, I hate subtraction, change to radian mode. I hate subtraction, change to radian mode. Now, if they caught me or if they saw me, that could have negated all of my students. Okay, but they never caught me. They never saw me. And I guess apparently my students were laughing the whole time now because they knew what was happening. But my mantra is I hate subtraction. Subtraction will screw me up every single time. So slow down when there's a subtraction problem. So it looks something like this. So you say 4x plus 3, subtract x minus 8. But remember, there are parentheses. It's the quantity. You're subtracting all of the quantity, and you keep the denominator, 2x minus 1. Well, we studied this way back in chapters 4 and 5, I think. What do you do with a minus sign in a quantity? You distribute it. Okay, that minus sign distributes to that quantity. So technically, you have 4x plus 3 minus x plus 8 over 2x minus 1. So you distribute the minus sign into the second quantity. Okay, that's why it's tricky. People forget to distribute. They just see minus x, and they forget to go minus x, and minus a minus 8 is a plus 8. They forget to do that. Okay. Add like terms, 4x take away x is 3x, 3 plus 8 is 11. So plus 11, keep the denominator, 2x minus 1. There's your answer. And again, it does not reduce. This one doesn't. So 2 basic questions. They're pretty straightforward. I'm going to do one more, and then we'll move on to much more difficult problems. But these already had a common denominator, or they already had the same denominator. So all you had to do was add or subtract the numerators together, keeping the denominator. Whatever the denominator was, you keep it. Okay. And then try to reduce it, but none of these reduced. Okay. Now I need to erase my notes and erase some of these problems, or a little bit of it, for my next example. Anybody have any questions so far? I do. How come I was never fired at Pali High School? I should have been. I pushed so many boundaries, it wasn't even funny. But, okay. Last example here. Okay, 2x squared over okay. So we'll put it on pause. You guys try that problem as best you can. Okay. So the 2 denominators are the same, which is cool. So the rule is subtract the numerators, keep the denominator. Okay. And then by now you guys should be going, whoa, wait a minute. that was too easy. I really didn't do anything. Okay. Does it reduce? Remember, in algebra, reduce is the same as factor. So when you're asking yourself, can I reduce this fraction? You're actually saying, can I factor it? Yes, you can. So let's look at the top. We can take a 2 out, leaving x squared minus 1 over x minus 1. But wait, we can factor the numerator even more. So the 2 is already out. The numerator, the x squared minus 1, is a dose. It's a difference of two squares, D-O-S, dose. So it becomes x minus 1, x plus 1, all over x minus 1. Okay, so we can go, oh, now I can cancel those two x minus 1s. And I'm left with, technically, 2 times x plus 1 over an invisible 1. The rule was multiply the numerator, so that's 2x plus 2, and we don't ever need a 1 in the denominator anymore. So that would be their final answer. Okay, so again, the two denominators were the same, so I just subtracted the tops, the numerators. But then I said, oh, wait a minute, it might reduce. Reduce means factor. In algebra, it does. So we factored it, took out a 2 that they had in common, and said, oh, dose, I factored the dose problem, and now I can see parts of it canceled out. Okay, so then I canceled it out, put it all back together. There's my answer because I distributed the 2 into that quantity. Is that okay with everybody? I'm going to move on to more difficult problems unless you yell at me and have questions. Okay. Then we'll get an erase and go to more difficult problems. These, if you want to go back and add to your notes, these were all from chapter 8.3 in MOM, section 8.3, because they started with the same denominator. They all had a common denominator at the very beginning of the problem. So you didn't have to do any work. You just added or subtracted the numerators and tried to reduce it if you could. Okay, this is section 8.3. They already had the same denominator. 8.4, they will not have the same denominator. Okay, so here we go. Okay, so chapter 8.4, we want to add or subtract fractions with unlike denominators. Unlike means not the same. Remember, you can't. You can't, okay? If you tried to add 2/3 plus 1/4, okay, you can't add them. Okay, now here's a slick way of doing this problem. Does everybody understand that you can't add this? You can't say that this is 3/7. You can't go 2 plus 1 is 3, 3 plus 4 is 7. Okay, the fundamental rule for adding or subtracting fractions was the bottom number has to be the same. Has to be. Okay, and you can't violate that rule, and there's no trick to get around it. The bottom number has to be the same. Now, we give all kinds of stuff. I know I talked about this earlier this semester, but it's coming back now to bite us again about, oh, we're always worried about getting the lowest common denominator. And oh, what do I get? Well, the easiest way to add fractions, okay, number one is on your calculator, but your calculator won't do what we're going to be doing. But the easiest way is just to use the other denominator. So if you multiply this by 4 and 4, and you multiply this by 3 and 3, remember, you always have to multiply. You're technically multiplying by 1. So you're changing this into 8/12, but 8/12 is equivalent to 2/3 because all you did was multiply by 1. You changed its look, but not its value. It looks different, but it's worth the same amount of money. 2/3 and 8/12, because you actually only multiplied by 1. 4 over 4 is 1. Same thing here. This becomes 3/12. Again, it looks different. 1/4 and 3/12 look different, but they're worth exactly the same because you only multiply by a 1 to top and bottom, always top and bottom. Okay. Now, look at what I did. No thinking is involved. Just look at this denominator, use it over on this fraction. Look at this denominator, use it on this fraction. And look what you have. You have a common or a same denominator. So when you add these, you technically say 8 plus 3, keep the denominator 12. Okay, so the final answer here is 11/12. And you can confirm that on your calculator. Okay, because it will do arithmetic fractions. So what happens if you have 5 over x plus 2 plus 3 over x minus 7? What happens if the two denominators are not the same? They have to be the same. They have to be the same. So you can use the same reasoning that we used here. You can just say, oh, man, I'm going to multiply this one by x minus 7, top and bottom. And I'm going to multiply this one by x plus 2, top and bottom. Because technically you're only multiplying by a 1. Yes, it's a weird looking 1, but it's a 1. And this is a different form of 1. So when you put this together, this becomes 5x minus 35 over x minus 7, x plus 2. Remember how we said you multiply out the numerator, but you leave the denominator factor? Plus, this becomes 3x plus 6 over the same thing, x minus 7, x plus 2. So check it out. Now the two denominators are the same. Okay, how did I get them the same? I used the other denominator as a guide to help me multiply. Add things together. 5x and 3x, I'll skip the steps. It gives me 8x. Negative 35 plus 6 is minus 29. And I keep the denominator, x minus 7, x plus 2. And I'm almost in the glare, but that's it. And that's the final answer. So that's the easiest way to add fractions. It's not going to stay this easy, guys. It's going to get messier. But right now, if the two denominators are not the same, the easiest way to do the problem is to use the other denominator as a guide. So this one multiplies top and bottom by the x minus 7. This fraction multiplies top and bottom by the x plus 2. And yes, it screws up the numerator, but we don't care. The rule was the two denominators have to be the same. And since they have the same factors, I can see that they're the same. Okay, questions? All right. Then let's try you guys doing one of these on your own and see how you do. Okay. 3x over 2x plus 1 minus 4 over x plus 3. 3x over 2x plus 1 minus 4 over x plus 3. Try and add those two together. Okay, so if I use, I recognize the two denominators are not the same, but I have to make them the same. So the easiest way is to multiply this by x plus 3, whatever that is, and multiply this one by 2x plus 1, and good planning, Foster, 2x plus 1. So if I do that, I end up with 3x squared plus 9x over 2x plus 1 times x plus 3 minus, I have 8x plus 4 over 2x, well, x plus 3 and 2x plus 1. So my denominators are the same. It doesn't matter the order that you write these two, because the two factors are the same. Okay, x plus 3, 2x plus 1, they're the same. If you multiply them out, they'd be the same. Except this has subtraction. So the old rule, I hate subtraction. This subtraction symbol distributes into all of that. So this next step might look something like this: 3x squared plus 9x minus 8x minus 4. Because the minus sign distributes into all of that quantity over this mess: 2x plus 1, x plus 3. Now I am skipping a few steps, so if you need me to explain more or show more steps, I'll be happy to. But the key was the subtraction distributes and changes those, the 8x and the 4, into minuses. So now we get like terms. So we have 3x squared plus x minus 4 over 2x plus 1 times x plus 3. Now, okay, for now, I'm just say that's your answer. I don't believe it reduces, and I don't want to waste your time right now trying it. We got bigger fish to fry. But that's your answer. I don't think, I'm pretty certain it does not reduce. Okay. I'm very certain it does not reduce. Somebody will prove me wrong. Okay, so I need to move on because these are still pretty easy problems. You just use the other denominator to guide you. You multiply by the other denominator to ultimately get the same denominator. Now, the difficulty level is going to kick up a notch on my next examples. So how are you doing on these?
I had a question.
Sure.
So when you barely start out the problem, how do you find the number to multiply it by?
You use the other denominator. Remember this, what was this first problem? Do you have that? I had to erase it. It was something like 5 over x plus 2. Is that right?
It was
Plus
5 over x plus 2 plus 7 over x minus 7.
7 or 3?
7.
7 over x minus 7? Really?
It
Oh,
was
sorry, it was 3
5
over x minus 7.
Okay, 3 over x minus 7. Okay, that's what it was originally? 5 over x plus 2, 3 over x minus 7?
It was 5 over x minus 2.
Oh, it was?
Oh no, I'm sorry. That's right. Sorry.
Okay, so your question was, how do you know what to multiply by? You use this denominator. What I did is I just said, take this whole thing, this x minus 7, and multiply top and bottom by x minus 7. So I use this denominator to multiply this fraction, the other fraction. So when I go 5x minus 7, that's how I got 5x minus 35 here. And then for the other one, you use this denominator to multiply this fraction. So you multiply this one by x plus 2 to top and bottom. So you get your visual clue from the other denominator. Does that answer your question or not?
Yes. Thank you.
You sure? I mean,
Yes, it does.
okay, because I did the same thing here. I have a 2x plus 1, but notice I multiplied by x plus 3. I used this denominator against this fraction. And then I use this denominator against this fraction. And then there's all kinds of crummy algebra in between. Okay, good clarification, guys. This gets confusing, and it will get a little bit more confusing in my next example. So any questions you have, I would love to clarify now. Okay. This is what you want to use if you possibly can, because this technique of using the other denominator to guide you, okay, is really, really, really easy to do, and it's what everybody does. There's a more complicated way, but this is the easiest way. So my next examples are going to be messier, much messier. So hold on. This is still part of chapter 8.4. We still have unlike or not the same denominators. So suppose I had 5 over 3x plus 6 minus 9 over 2x plus 4. Okay. Now you could use that technique I just showed you a few seconds ago, but I want to show you a slightly different technique. Okay, that's going to then be useful as my problems get more and more complicated. Notice something. This factors into 3 times x plus 2. This factors into 2 times x plus 2. So the denominators aren't totally different from each other. They got a little bit in common. A little bit. They both had an x plus 2 in common. So remember, I'm a mathematician. I'm lazy. What's the lowest thing I can multiply by to make these the same? What I'm talking about is, okay, this, if I multiplied it by 2 on top and 2 on bottom, and if I multiply this by 3 on top and 3 on bottom, now the denominators would be the same, because I took a second to factor them and recognize, oh, look, they both happen to have an x plus 2 inside of them. So they already have something in common. They already share something. So all I got to do is figure out, okay, what else don't they have? This needed a 2. Again, using the other denominator to guide me. This one needed a 3. So I put all this junk together. So I have 10 over 6 times x plus 2 minus 18. No, not 18, dummy. 27 over the same thing, 6 times x plus 2. 2 times 5 is 10. 3 times 9 is 27. So now I can subtract these. Now that the denominators are the same, I can subtract the numerators. 10 take away 27 is negative 17 over this thing, 6 times x plus 2, whatever that is. So what's different about this problem? I factored the denominators first and noticed that they already had something in common. So I didn't have to worry about that. They already were somewhat alike. They weren't completely alike, but they were awfully close to being alike, the same. So I just worked to make them the same. All right. 6 over x squared plus x plus 5 over x squared minus 1. Okay, hint, I'm going to interrupt you in a moment. But hint, factor the denominators and think about what you can do to make them exactly the same. Let's pause for just a second while you. All right, I know you're probably not done, but what I really wanted you to was to think about it. If we take our denominators, this one we can factor out an x, leaving x plus 1. So this fraction, the first fraction, when we look at the denominator, it factors that way. Plus, this fraction is a dose, so it's going to be x plus 1, x minus 1. Okay, so if we look at our work, we can see that they already share an x plus 1. So I don't need to use that anymore. They already have that in common. They're already the same. So what is the first fraction lacking? What does it need in the denominator to be the same as this?
Negative.
Okay, it needs an x minus 1. what does the second denominator need to be the same as the first denominator? What's it lacking? An x. Notice the question I'm asking, because you're going to have to ask yourselves that same question. Okay, it's after I factor the denominators, I can see how they have something in common and how they're different from each other. And so my question was, what was this denominator lacking that this denominator had? That was x minus 1. And then what was this denominator lacking that this denominator had? And that was the x. So that question, what was the denominator lacking, is critical. You have to ask that question. That's how you figure out what's missing. So we put all this mess together. So we have 6x minus 6 over this whole stinking thing, x times x plus 1 times x minus 1, plus 5x over x times x plus 1, x minus 1. Notice the denominators are now the same. All of this work, all of this extra work is meant to get the same denominator. The numerator is all screwed up. We don't care about the numerator. The rule was the denominators have to be the same. So now we add like terms. The only thing I can add is 6x and 5x makes 11x minus the 6. And I just keep the denominator, x times x plus 1 times x minus 1. And that is my final answer. So, pretty common kind of problem, upper level, where you first factor the denominators and say, oh, look, they have something in common already. So what was the first fraction lacking that the other one had? And what was the second fraction lacking that the first one had? That's the game. All right, I'll be quiet while you guys formulate a question. Any questions at all? Anything? Okie dokie. Okay. Usually we take a break. What I would like to do is push through and get out of class a little bit early. Okay. I want to do 1 or 2 more questions on this. One more topic, pretty straightforward, and then we're going to be done for the night. We'll be done before 8:30. Okay, at least that's what I'm hoping. So if you need to take a break, go ahead, but I'd like to push right on through just to get us out. Time, I don't know. Is the game over? Anybody watching the baseball game? Okay. I'm not foolish enough to believe that everybody is listening to me all the time.
Will the quiz have this also?
Tomorrow's quiz?
Yes.
Yeah, but it'll be simpler than, it'll be more along the lines of the first problems, which all you had to do is use the other denominator, not have to factor this. But remember, tomorrow you will be able to use your notes.
Right on. Thank you.
Okay, so don't panic too much. All right, so let's have you guys try this one. 2 over x squared minus x minus 12 plus 3x over x squared minus 16. Okay, so let's pause. So while the recording was turned off, I factored the denominator, and I can see now that they already have a little bit in common. So now I play the what's lacking. So the first fraction is lacking an x plus 4. So I simply give it to it. X plus 4 on top, x plus 4 on bottom. The second fraction is lacking an x plus 3. Now, where you stick the x plus 3 or the x minus x plus 4, like here, it doesn't matter. Okay, I'm trying to emphasize that you multiply the top by x plus 3 and the bottom by x plus 3. Okay, and the top of this one by x plus 4 and the bottom of this one by x plus 4. And where you put the x plus 4s and the x plus 3s, that doesn't matter. So we put all this together and we end up with 2x plus 8 on top. And we get this big ugly mess, x plus 4, x minus 4, x plus 3. Thank God we do not have to multiply that together. Plus this mess, 3x squared plus 9x, because we distribute over the same mess, x minus 4, x plus 4, x plus 3. Oops. So is that okay with everybody? Where did I magically pull x plus 4 from? The other denominator. Where did I magically pull the x plus 3 from? Where did it come from? Okay, the other denominator. So I'm still using the other denominator to help me make these two denominators the same. All right, adding like terms in the top. So on top, we have 3x squared plus 11x. 2x and 9x is 11x plus the 8. And keep the denominator, x plus 4, x minus 4, x plus 3. And that is my final answer. Yes or no? Anybody, any questions anywhere? Okay, then we're going to move on to tonight's last topic. That leaves us 2 topics to learn tomorrow night. Okay. One of tomorrow night's topics is relatively easy, and one of tomorrow night's topics is, oh, how do you say, uglier than sin? Okay. So I do hope you're there tomorrow night. It's going to be really, really kind of messy. So in chapter 8.3 and 8.4, we learn to add and subtract fractions. And the key rule was they must have same denominator. And all of those other tricks that I was doing, okay, was to get the same denominator. And I suppose you could say one of the keys is to use the other denominator. That's what we always did when we had a couple fractions up there. We looked at the other denominator for some kind of guidance. And sometimes we factored them. All right. 8.5. Chapter 8.5. It's titled Complex Fractions. And there's a question last night. It was, when are we going to ever use this? Well, complex fractions are going to be used quite a bit in trigonometry. Trigonometry is all about ratios. A ratio is a fraction. And they're going to be having fractions divided by fractions all over the place in trigonometry in Math 104. You know, you guys think it's about triangles. Well, it is, but it's also about fractions and fractions dividing fractions and fractions multiplying with fractions. Okay. And a complex fraction is a fraction divided by another fraction. And if you stop and think about it, we've already seen that tonight. Remember my example when I started at the first of class where I had f of x divided by g of x? Okay, that was an example of a complex fraction because f of x was a really ugly rational expression. Then we had to factor it all over the place. G of x was another rational expression. But eventually, okay, we took it apart, and the key was because it meant f of x divided by g of x, and we already knew how to do that. So even though it looks like a fraction, we took it apart, okay, and it made it relatively simple. Now, it's going to turn out that there are several different methods to use to simplify complex fractions. Several methods. This is one of the methods. This is one of the methods where you just simply take the problem apart and write it as a division symbol. And that usually works about 90% of the time. Occasionally it doesn't work, and whether I get to it tonight or tomorrow night, we'll study when it doesn't work. Okay, but a complex fraction is a fraction divided by another fraction. Okay, a fraction over a fraction. So it might look something like this is a very simple complex fraction, 4 out of 6 over 8 out of 9 or something like that. That's called a complex fraction because the numerator is a fraction, the denominator is a fraction. And the easiest way to do this problem for now is to say this is 4 out of 6 divided by 8 out of 9, because the fraction bar means division. Okay, and you guys now know how to do this. This is 4 out of 6 times 9 over 8. We've talked about cross-canceling, reducing, all kinds of things. I don't know what this is. This is 36 over 48, which reduces to 3 over 4 eventually. You can do all that. Okay, whether you cross-cancel or use your calculator, whatever, when it's arithmetic numbers, okay, you can use your calculator. Your calculator will do all that. But what if it's not arithmetic numbers? What if it's something like this? 2 over x squared minus 1 over 3 over 4x plus 4. What if it's something that looks like that? Okay, well, what did we learn over here when we did that problem at the very start of class? We didn't panic, even though it looks really scary. We took it apart and wrote it as a division. So I'm going to pause it while you work on that. Okay, so I started this problem with the recording turned off. First thing I did is I took the complex fraction and wrote it in a more normal way using the division symbol. Next thing I did was I flipped the second fraction and changed it from division to multiplication, but simultaneously I factored everybody that could be factored. I knew I have to factor, so I just started factoring everybody. But I also knew that I had to flip the second fraction. So I did that. So I'm combining a couple steps here. Change the fraction bar into a division symbol. The division symbol becomes a multiplication symbol, but we flip. And then I factored everybody. Okay, now I'm looking to see who cancels. Okay, the x plus ones cancel. Okay, nobody else cancels. That's cool. So the rule was multiply the tops. 2 times 4 was 8. Leave the denominator factored. Now, if you want to multiply those together, you can, but I'm giving you the option of not multiplying the denominator. Okay, but you have to multiply the numerator. 2 times 4 was 8 because we canceled out the x plus 1s. On bottom, we have a 3 times x minus 1. If you want to distribute that together, you can. If you want to leave it factored, you can. And that's it. Now, there are other ways of doing this. There are some trickier ways. I'll try and get to those a little bit tomorrow night and a little bit next week. But this should get you through about 99% of everything in section 8.5 on MOM. Okay. Whatever. Tomorrow night we have 2 lessons to do and some review, and we have a quiz, but you can use your notes on the quiz. So don't panic. Okay, at all. And then I said tonight for for taking roll, I was to take roll tonight. So here's what I want you to do. Okay. I want you to email the answer to my Mesa address, which is lafoster@sdccd.edu. That's the one that everybody keeps emailing me at, but I just want to make sure that that's the one you send it to. Email that answer to me before 11:59 p.m. tonight. Okay, not in the morning. Okay, not I woke up in the middle of the night and remembered, or I fell asleep. I want that before midnight tonight. Okay, and I want you to solve this problem. Absolute value of 2x minus 3 equals 33. And that's it. And good night. See you guys tomorrow night at Mesa. Bring your mask.
Thank you, Professor.
Good night. You're
Thank
welcome.
you.
Night night.
Thank you. Have a good night.
You too. Thank you. Bye-bye.